In the last video, we had a left-hand side that looked like 0 to L of W sub I n sub j dx plus alpha delta t theta dwi dx dnj dx dx, make this 0 to L, times t of j n plus 1 plus our boundary term w sub I n sub j dtj at n plus 1 dx evaluated at 0 and L. Let's leave the boundary term. We will leave this until we actually look at all of the boundary terms. So until we evaluate the boundary conditions. And instead, we'll focus on the first two terms. So if we do that, what we see is that the integral of 0 to L, alpha delta t theta dw sub I dx dn sub j dx dx, this is familiar. This is what you worked with, except for the coefficients. This is what you had for the 1D steady multiple material problem. What's new is the alpha, but you'll select that. The delta t, you'll also set this. And of course the alpha is the material property. So this will be, we will get this from tables. So we know how to compute this entire term, which means we really want to focus on the temporal term. So I'll just call out again that this is the spatial term and this is the temporal term. And calling again or paying attention to the fact that the thetas go with the spatial term. We know that when we look at the temporal term, we're going to use a finite difference approximation and we will evaluate T sub j at n plus 1. That's the new temperature that we're looking for, and we will have a Tj at n, which is the previous time step, and that's how we're evaluating the temporal term. So the thetas are really determining where between those two temperature terms, the previous or the current one that we're looking for, where are we going to evaluate the spatial terms. So our term, once again, 0 to L, W sub I n sub j dx. And just as before, we're going to break up the elements so that we have 0 to xa, w sub I n j dx, plus xa to xb, w sub I n sub j dx, plus xb to xc, plus ... until we get all the way to the end. So just as we did before, we're going to do this element by element. And if we do this element by element, let's look at what that looks like. How do we evaluate this integral? Consider two cases. One, I equals j, and two, I not equal to j. So what does that look like? Well, I equals j means that we have xa to xb w1 n1 dx, which is also equal to xa to xb w2 n2 dx. And for I not equal to j, we have xa to xb of w1 n2 dx is equal to the integral of xa to xb, which is w2 n1 dx. And just as you look at these, you should think to yourself, I know what the definition of w1 is. I know what the definition of w2 is. Consider the first case. So the first case was I equals j. So that means what we have is we have xa to xb, w1 n1 dx. The same will be true for w2 n2. Now, let's substitute in for w1 and n1. So that means we will get the integral from x equals a to x equals b, that's our element, of x2 minus x over the element length, which is xb minus xa, times x2 minus x over xb minus xa dx. So the first thing that we're going to do is we're going to say, okay, let's take out 1 over xb minus xa squared. Now we're left with the integral xa to xb of x2 squared minus 2x2x plus x squared, parentheses there so we can dx. Step 1, integrate that. Step 2, evaluate at the limits and subtract, just as you always do, standard calculus. Step 3, a lot of algebra. In fact, so much algebra that the expansion of all of this in terms of the algebra has been left for a different video. What happens is, after all this, what we have is that the integral of xa to xb of w1 n1 dx is equal to xb minus xa over 3, which, as we know, is the element length over 3. If you follow the same analysis for the case for I not equal to j, xa to xb of w1 n2 dx is equal to xb minus xa over 6, which is the element length over 6. So these formulas are shown on the sheet that I've attached of the 1D formulas, and you'll find just as the formulas for dw, wi dx, dnj dx were there, the formulas for the various integrals are also there. Okay, so now if we go back to look at what our A matrix was, let's just write that again so that we have it. It was 0 to L of wi nj dx plus integral 0 to L alpha delta t theta, all of which can come outside of the integral, times wi dx dnj dx, again all can come out of the integral dx, and all of this was multiplied by tj. All of this was the coefficient, the matrix coefficient for tj of n plus 1. And this was our aij, but it's also known as the left-hand side. And you can use either name in the code. In fact, you can use any name in the code that you want. It's often referred to as aij because people think of matrix problems as being ax equals b. Okay, so we have the terms. We know how to compute every term that's in this matrix. So let's just look for a minute at what the pseudocode looks like. Just as we said when we started to do the derivation, we're going to go element by element. So that means that we're going to start with for 1 to n elements. Nothing's changed there. We need to compute the element length. I'm just going to call it ln because I'm going to be writing it a lot. Okay, so that's fine. Nothing's new. Then we're going to say for I equals 1 to the number of nodes in the element. Now, the first thing we need, just as before, we need our I global for the matrix. And that's going to be a function of the element array for L, comma, I. And then, just as we had before, well, if I is equal to 1, then we have dw dx is equal to minus 1 over ln, else dw dx is equal to 1 over ln. So far nothing's changed in our formulation. Okay, so now let's look at j. This is where things do change, so I think I'm going to put it in a different color just to call it out. Okay, for j equals 1 to the number of nodes, we once again need to compute our j global, and that's a function of the element and j. That's how we'll get our j global. Now, if j is equal to 1, dn dx is equal to minus 1 over the element length. Else, dn dx is equal to 1 over the element length. So far, nothing's changed. Now, I'm going to continue. I want to continue on the same page, so I'm going to put a dividing line here. But I'll continue writing the code in green so that we know it's still within that j loop. Okay, we have just what we had before. J global, we have dn dx, but now we have if I equals j, we have wi nj is equal to L length over 3. Else, wi nj is equal to L len over 6. And now we compute A of I global, j global equal to A of I global, j global plus wi nj plus alpha delta t theta times dw dx times dn dx times ln. The question is it clear to you why this new piece has to be in the j loop? Hopefully it's clear from what we did previously when we computed wi nj. We made the two cases. If I was equal to j, then it was element length over 3. Otherwise, it was element length over 6. But you need to know both I and j in order to be able to make that determination. So this has to be within the j loop. So there we are. We have the A, I global, j global matrix all set for the time-dependent problem. Let's go ahead and just look at the right-hand side. So the right-hand side, there are a couple of things that are new here that need to be mentioned. Previously, we solved ax equals b. And b, this had our boundary conditions. And that was all we had on our right-hand side. But now, the right-hand side is a matrix. Now the right-hand side has 0 to L, w sub I, n sub j, dx, minus 1 minus theta, alpha delta t, dw dx, wi, dnj dx, integral 0 to L, dx, and all of this is multiplied by tj at n, where tj at n is our previous time step. So now we have this matrix that we have to build out, and what that means is that, 1, we need to consider right-hand side of I global, j global equal to, remember we're summing again, so we've got the right-hand side of I global, j global plus the terms. Okay, so that's one thing we have to consider. 2, if you look at this equation that makes up the right-hand side, first of all, look here. The temporal term, it's the same temporal term as what we saw in the A matrix. How about the spatial term? The spatial term is almost the same. There's a 1 minus theta instead of theta, but it uses all of the same terms. So it has the same terms, the same spatial terms as in A. There's a sign difference, and there's a 1 minus. So what does this suggest to us? So we had pseudocode. Let's write this as L equals 1, 2, we're going to say any L. I equals 1, 2, num nodes. J equals 1 to num nodes. And you will know that I'm writing this to collapse everything so I can fit it in, but all of the pieces that we had in the previous pseudocode about 3 slides ago, it is exactly what's in there. Now we would have our A, I global, J global. But now we need to have right-hand side of I global, J global. Just as before, because we're summing, we need to have right-hand side of I global, J global, plus Wi and J minus 1 minus theta. And you when you go to write your code, you can rearrange these minus signs as you wish. Just make sure that you've got the right sign, or you'll get the wrong result. Delta t, dw dx, dn dx. Oops, I'm going to put these in parentheses because element len. So that's the whole right-hand side. That's how you're going to create the matrix. The next video will discuss the solution, the boundary conditions, and the time stepping.